Okay, I'm just preparing to go on YouTube now. Okay, I'm just preparing to go on YouTube. Okay, hello everybody, and welcome to our 11th Fault2SHA learning series. I'm absolutely delighted today to have Graeme Weatherill with us. He's coming to us from his current position at GFZ, the German Research Centre for Geosciences. Prior to that, he worked for 7 years in GEM, the Global Earthquake Model. So that's where a lot of his experience in seismic hazard has come from. And before that, he has a PhD in seismic hazard and a master's in geophysical hazards as well as all his sort of GEM-related work. He's busy publishing with nearly 1,500 citations. So he's particularly informed on the subject of source models for seismic hazard. So Graeme, thank you so much for talking about this. And I think it's a really useful topic in terms of taking what a lot of the people in our community do and actually applying it to the seismic hazard space. If anyone has any questions, Graeme will be delighted to take them at the end, but he'll go through his presentation first and then we'll open it up. So Graeme, thank you again so much. Really looking forward to your talk and appreciate all the time you've spent preparing and coming for us today. And just a quick warning that both Graeme and I are having storms outside. I'm sure a lot of you are being affected by the storm. So if we do suddenly lose contact, just bear with us, wait a moment and we'll join again, because I have been experiencing power cuts. So hopefully we're okay, but just to warn you of that. So with that, again, thank you so much to Graeme, and I will hand over.
Thank you very much, Joanna. Thank you for the introduction. And thank you for everyone joining, both on Zoom and on YouTube. And to sort of give a sense of what I aim to cover in this presentation, it's actually going to be not so much a presentation on sort of active faulting and geology. This is going to be, it'll come up, but it won't be the main focus. What I'm really focusing on is really how we get to the process of building seismogenic source models for PSHA, focusing particularly on earthquake catalogues, the sort of issues we have in constructing them, interpreting them, and then how we try and sort of characterize seismic sources in different regions of the world. I'm going to try and draw and show some examples from different PSHA models around the world. So to start off, just to let's give ourselves a little bit of context on what we're trying to do with seismic hazard assessment, what's our main objectives. Consider the case of a city in the country that I'm currently living, which is the city of Cologne in Germany. And for building design or for sort of decision-making purposes, one of the things that we're sort of trying to provide for the community are the estimates of what's the probability of the ground motion exceeding some given level in the next sort of 50, 100 years or further and further in the future. And to do that, when we do this in practice, our first sort of step is to try and compile and construct all of the seismicity and the geology data we can find in a region. And what we're trying to do here is to create what we call these seismogenic source models. So the seismogenic source model, it's important to recognize it's not just a model of the active faults itself. It really has to be a model, something that can describe all of the potential earthquakes that we believe can affect the site in question. And seismogenic source models have two components. The first component is a characterization of the rate, so the rate of earthquakes above some minimum magnitude of engineering interest, and a probability density functions to describe the probability of a given magnitude from each one of these sources. So we have the rate and the probability that we have a certain magnitude, and the probability that the source or that the source to site distance takes a certain value R. So this is the seismic source model component of probabilistic seismic hazard analysis. And once we have this, the last part, or the important piece, is the ground motion model, which is basically what we use to describe the probability of our ground motion exceeding a certain level, given the occurrence of each magnitude and source to site distance. And for more information on ground motion models, I would strongly suggest to look at a lecture from John Douglas a couple of months ago. So this is the objective here. So seismic hazard analysis is in two parts. We have the seismogenic source model, which is trying to construct our models of the rates of seismicity and the probabilities of given magnitude, and we have the ground motion models. And today I'm just focusing on the seismic source modeling part. In the end, what we come up with when we apply this process is a distribution of seismic hazard curves. So for each different level of ground acceleration, we have a probability of exceedance or rate of exceedance, which is what forms our seismic hazard curves. And these then yield the products that you're probably quite used to seeing. So seismic hazard maps, uniform hazard spectra, or disaggregation that show the controlling sources or the scenarios that affect the seismic hazard at the site the most. So what are the components of a seismogenic source model? Well, the first part is we need a seismic source geometry. We need something that describes the location or position of where future earthquake ruptures will come from. And this can be, or take the form of a point source, so earthquakes occur from a single location. It could be a fault source, so an actual sort of 3D fault surface that will generate ruptures in the future. And, or it can be an area source, so a source where we assume that earthquakes can occur uniformly within the region. As we've seen from the previous slides, we need an activity rate, so a rate of earthquakes greater than or equal to some minimum magnitude, and we need a magnitude density function, something that gives us the probability of occurrence of each magnitude or magnitude in the range of interest or the range of magnitudes that we're considering in our model between our minimum and some maximum value. We also need a magnitude scaling model, so something that relates the magnitude of the earthquake to the corresponding size of the rupture. And depending on what sort of model you're looking at, we need some sort of information to describe the style of faulting, the rupture mechanism, so the rake of the ruptures, strike, dip, if this is not already inferred from the geometry. And the final step is we need a temporal occurrence model. So far, I've talked in terms of rates and activity rates, but actually what we do in the end is to transfer this into probabilities of exceedance in some sort of rupture, in some sort of time, period. And this is where we often make the assumption of a Poisson temporal occurrence model, but others can be found in the literature. And I'll talk a little bit about that in due course. So where do we usually start with this? Well, our starting point is usually, or one of the first data sets we consider, are harmonized earthquake catalogs. And we'll see in the next few slides what we really mean by harmonized earthquake catalogs, the harmonization process and the sort of challenges we face. A second sort of major data set we have, not in all regions of the world, but in many places now, we have active fault models, so models coming from structural geology or active fault maps. And then we have a sort of a third category of general geophysical models, so it can be stress, it can be bedrock geology, strain, GPS, models that tell us something about the potential seismogenesis of a region, but whose role can be quite variable, and we see a little bit how we could try and use this. So starting then with the idea of harmonized earthquake catalogs, what do we really mean by a harmonized earthquake catalog? Well, it's a catalog where for each earthquake we have a unique or a preferred location. We have a common magnitude unit, usually equivalent to moment magnitude or MW, and we have an estimate of spatial and temporal completeness. And by completeness, what I really mean is the magnitude above which we are certain, or at least highly confident, that our catalogue is capturing every single earthquake that has occurred in that time period or in that spatial window. And there are many sort of uses of this. We're going to focus today mostly on the characterization of earthquake recurrence in PSHA. If we want to try and characterize this magnitude density function, we need a sort of harmonized catalog to do so. But it's also important in ground motion modeling. We also need to have, if we want to understand how ground motions scale with magnitude, we need to have a common magnitude scales. And more recently, we've seen this becoming important for sort of shake map and rapid loss estimation or operational earthquake forecasting. So, taking a look at where our data comes from, or the sort of time period over which we have information, we tend to sort of characterize our earthquake catalogue, sort of our record of earthquakes in a region, into sort of two distinct periods. The historical period, so this is a period in which our earthquake information is coming from sort of historical records and macroseismic data, and the instrumental period. The exact duration for which these two periods apply for a region can vary from region to region. In our best cases, we may have historical records going back a couple of thousand years, though really only sort of parameterized or parameterizable for about 1,000 years. And exactly when we transition from historical to instrumental can often depend a lot on the history of a region in terms of when local seismic networks are deployed. But our instrumental period tends to cover sort of more or less to the start of the 20th century, and the historical period a little bit before that. So when we're trying to compile a catalogue of earthquakes, I'm just going to start by talking about the historical earthquakes. So we have this distinction is not always sort of clear, not always accurate. But by historical earthquakes, I mean earthquakes that are parameterized or constrained by macroseismic data. So historical earthquakes are ones that we understand and we know about from written descriptions of historical earthquake damage that can provide an insight into the impact of event and the spatial extent of the ground shaking. And this sources for this can come from historical chroniclers, so people writing at the time of the event, monastery records, or records from other sorts of religious buildings or religious institutions. And by the sort of the mid 18th century and later, we start to have early newspapers and almanacs. And where written accounts are abundant and relatively descriptive, we can make specific estimates of intensity at certain places. So I'm just showing an example here, an example from the 1884 Colchester earthquake in the UK, where we have quite an abundant set of written descriptions of damage. And this allows us to be able to sort of assign what sort of level of damage and what sort of intensity has occurred in the various towns and villages around the earthquake. Some of you are probably already quite familiar with the macroseismic intensity, but for those of you who aren't, this is really, it's a sort of semi-qualitative scale, one in which we assign a sort of an integer value between 1 and 12, based on interpretations of people's felt reports of the earthquake itself. So, and this varies from sort of 1 or 2, where we really have earthquakes that are not felt or only detected by instrumentation or maybe barely felt, through to sort of 4, 5, and 6, where we start to get damage varying from sort of just minor cracking in the walls all the way through to serious structural damage, and then all the way up to sort of 9, 10, and above, where we're talking about really sort of catastrophic levels of damage. So the modified Mercalli intensity scale is one of the most commonly used scales. But you also have an application in Europe is the European macroseismic scale, and this tries to give a more sort of nuanced and more careful classification of the different building types and the different grades of damage. But ultimately, these refer back to this 12-point scale. And these macroseismic intensity observations are particularly helpful for trying to understand, although the actual factors that may influence the intensity at a site can vary on many things, including local soil response, sort of buildings or little structures around. Generally, the distribution of patterns or distribution of intensities around the earthquakes give us a lot of strong indications about the nature of the seismic source, or the location of the source, and its magnitude. And this is the information that we try to exploit here to try and parameterize these historical earthquake catalogues to get an estimate of location and magnitude. And similar to ground motion models, there do exist in literature models describing how intensity scales with magnitude and with distance. Sometimes these are parameterized in terms of the actual magnitude scale, so the MW, or the moment magnitude of the earthquake, and the hypocentral distance. Sometimes these are parameterized in terms of sort of distance and epicentral intensity, so intensity close to the epicenter of the earthquake. The coefficients of these models tend to be region specific. And really how we retrieve the parametric information is to use relations such as those that you're seeing here in an inversion process, one in which we try and identify the potential location and magnitude that minimizes the discrepancy between the predicted field of intensity and the intensity observations, usually using some sort of sum of squares residuals. Some of these methods can account for orientations of the fault as well. Very often, though, they focus particularly on location and magnitude. In these cases, constraints on depths can be poor. Obviously, these models have a lot of uncertainty, particularly as you go further back in the catalogue when you're constrained by fewer and fewer data. And the accuracy can also vary depending on the circumstances. So when you have offshore earthquakes, or when you don't have a sort of a clear picture of the actual full sort of radial distribution intensities around the earthquakes, you can sometimes have problematic mislocations. But this allows us to basically take our reported earthquakes and turn this into parametric events that we can fit into our catalogue. So that's the historical side of earthquake catalogues. Now to focus on the instrumental side. So these are earthquakes where we have the magnitude and location are determined from recordings, from seismic waveform recordings on recording instruments. Now, often when we build seismic hazard models in practice, if we work in different parts of the globe, one of our sort of starting point, the place where we have sort of the largest volume of data, is coming from global data sources. And really the main archive here is that from the International Seismological Center, though you can also find global catalogues from the US NEIC, GEOPHON, and others. So these are catalogues that cover the entire globe. They're usually constrained from, magnitudes are usually sort of constrained from teleseismic waves. So they're often reported in terms of body wave, MB, surface wave MS, and moment magnitudes. And these catalogues, they are global in scope. So really they allow us, or they become the starting point for sort of building earthquake catalogues in any given region. But in addition to global earthquake catalogues, we also have local data sources. So there are national or regional recording networks, and data is usually available from the websites of these respective recording agencies in each country. Some of them do feed into the ISC bulletin, and so they might be accessed directly via the ISC too. They usually rely on better station coverage, so you should have a high density of sensors and therefore a higher resolution local shallow shear wave velocity model. So you should, in theory, potentially have higher accuracy locations, so that can obviously vary from network to network, and a lower detection threshold, so you can pick up smaller magnitudes than you might do from teleseismic distances. And in these cases, the magnitudes tend to be reported in scales based more on short period motion, so local magnitude scale, local magnitude or body wave magnitude over short distances, or duration magnitude. So this really begins to introduce us to the problem we have when we're constructing catalogues, which is the magnitude problem. So magnitude measurements in different scales do scale differently from one another, and challenging the problem even more if we're trying to sort of mix data from different networks or recording agencies, even the same magnitude measures, so MB or ML or others, may actually differ between different networks and agencies. And usually what the problem we find, and it's illustrated well in this plot here from one you might see in seismology textbooks quite often, which shows the relative scaling between the different magnitude scales. So we have things like MB or ML, these body wave or high frequency calibrated magnitudes tend to saturate around magnitude 6 and magnitude 7, so they have a sort of upper limit as to where they're sort of most useful. We have surface wave magnitudes coming from teleseismic distances. They tend to sort of saturate around magnitudes of 7.5 and 8. So our global standard magnitude, the one that we sort of generally take as our sort of reference, is moment magnitude. But at the same time, there are global databases of this, like the Global Central Moment Tensor database, and several other networks now report this more routinely. But the threshold for estimating moment magnitude from global databases tends to be somewhere in the range of sort of 4.5 to magnitude 5. So we see we have differences in how magnitudes scale and how they relate to one another, and also the sort of ranges of values that they can cover. But if we want to estimate recurrence or understand how, for example, ground motion scales of magnitude, we need to render these events into a common reference scale. So our reference scale for this is usually moment magnitude, but it's important to recognize here that we're talking about this moment magnitude here as a proxy magnitude if it's been converted or determined from another magnitude rather than directly from a moment tensor. So how do we do this in practice? Well, in the ideal case, if resources were limitless, we would actually be sort of taking or going back to the original waveforms of the events and trying to harmonize the catalog by relocating the earthquakes and making re-estimations on magnitude. Very often in practice, that's not possible, either because resources and time are too limited, or because data is now no longer accessible, particularly for earlier periods. So what we're doing then often is something more of a data-driven approach. So we begin by starting to compile databases where we sort of integrate our different data sources, and we try and identify the common events. We try and identify those events where we have magnitude or location estimates from multiple agencies. This is something we do often by duplicate finding. It can be done sort of algorithmically if you're dealing with sort of tens and tens of thousands of events, or by inspection if you're dealing with a smaller number of events. And once you've done that, once you've built your sometimes quite substantial database, you can then start to sort of execute queries on this database where you can start to say, okay, find me the events from this magnitude scale, from this magnitude agency, and this other magnitude scale, ideally our target magnitude scale from another agency. And you can begin to extract this data and perform regression on this. And this is really a lot of what we do in sort of catalog harmonization, trying to understand the relation between magnitude scales from different agencies and use these to build conversion equations. We tend to use orthogonal regression, so we assume measurement error in both the variables, both the dependent and the independent variable. And it's always important when we're doing this to propagate the uncertainty that comes from the original magnitude estimates themselves, and the scatter, the large uncertainty that comes from the conversion relations. This is all very nice in theory. In the real world, we could be confronted with any number of challenging problems here. One of which, so we have example, a sort of good case. On the left, I have a conversion between a local estimate or a moment magnitude estimate from a local agency, one in Japan, with a global estimate of MW. And we find that on the left here, our magnitudes are scaling relatively well. So it's come quite close to the sort of a one-to-one scaling with low variability. On the right, we have a lot of noise. It's a conversion between a local and a sort of teleseismic magnitude, and you see that there's a lot of variability, a lot of noise. And in some cases, we really can't even make that much sense of this, or we can't even really exploit these sort of conversions for use in the catalog. So unless somehow we can sort of try and reconsider, recalibrate the earthquakes and regional waveforms, we're really sort of stuck not necessarily being able to do too much to bring this data in. And this can be sometimes why certain records, local networks or local catalogs can end up being rejected from use in a particular PSHA. Once this is done, then building the catalog is really, it is a flow chart. We start off with our database on our bottom left. So we have our huge database of all the different agencies and managed estimates for our earthquakes. We define these empirical models. We may fit them ourselves. We may use others from the literature. And then we're simply applying hierarchies for selecting the preferred agency or the preferred location and the preferred magnitude rules. We might sort of say, okay, if there is a moment magnitude from one agency, from GCMT, we take that. Otherwise, we go to this other scale from this other agency and apply this conversion, else if, and so on and so on. And making sure that wherever we can, we try and propagate the uncertainty. And the result of this should be a magnitude homogeneous catalog. But it's important to emphasize that except with the cases where the magnitudes come directly from the moment tensor, this is a sort of a proxy magnitude. There are often many problems we encounter in this. It's just an overview. We often have missing parameters. You can have timing errors that can mean that trying to associate magnitudes can be problematic. We have changes in network processing procedures, sometimes not always well documented or retrievable. You have cases or regions where you have too few events for regression or very large scatter, as we saw. We have regression models, or we can regress. We have models that might change with time, with region or depth, and we don't always know if these are real changes or just an artifact of a limited data set. And we have systematic biases in location, managed estimation, and so on. And we often have to try and take this into account to make our selection hierarchy change over time and usually over space as well. But so far, I've presented these magnitudes of the conversion issue as a problem. So if harmonizing catalogs are our sort of main target, this diversity in scales is a problem that we want to try and address by this sort of rendering into a common reference scale. But from a scientific point of view, it's important to recognize that differences between different magnitude values for the same earthquakes can actually provide some insights into the earthquake source and the potential attenuation characteristics of the region. So every magnitude estimate actually contains a little bit of information about the source that helps us understand a little bit more about what's going on in the earthquake. And this is relevant for ground motion prediction. It's not something information that we just want to always discard. And actually, one of the things that we're looking at now as a sort of ongoing research is to explore the possibility of multi-objective harmonization, really just using large databases of earthquakes and magnitudes and understand how the magnitudes may relate and scale with each other and how these might relate to other seismological properties that we can measure, with the objective then of trying to develop databases not just harmonized in one magnitude, but maybe even several magnitudes. So this is our catalog. If you apply this process, you should end up with our harmonized earthquake catalog. But then we encounter the problem that comes up a lot in seismic hazard modeling, is one of the biggest challenges we face, which is estimating our earthquake catalog of completeness. So completeness, if you recall, as I said earlier, it is the magnitude above which we expect or we assume that our earthquake catalog is recording or has registered every single event that's occurred. And this is something that we can address either at a sort of source level, something that really should be addressed in the sort of the source catalogs that would go into your harmonized catalog. But very often we have to look at this in terms of the harmonized catalog itself. And it's important to recognize that this completeness magnitude is obviously going to change with time. Our completeness threshold is going to get higher and higher. Usually, there are exceptions, but it will get higher and higher as we go further back in time. And it can also vary spatially as well. So there's two perspectives or two ways you can try and approach the problem to make sort of quantitative estimates of when your catalog is complete. And some of the most commonly encountered are methods that I would sort of describe as being expected rate methods. And what these are really doing here is breaking our catalog down into magnitude bins, maybe sort of half a magnitude unit or even less, and basically trying to look at the time period or making the assumption of a sort of stationary Poisson process to look at the time period above which our observed rate starts to fall below the expected rate that comes from a stationary Poisson process. And there's a commonly used methods in the literature, one by Stepp, 1971. But you can also do even sort of simpler analysis where you simply plot the cumulative number of earthquakes with time And you sort of begin to see, okay, when you might start to see changes or a time period after which you start to have relatively constant rates of earthquakes. And these give us indications as to when our completeness or when our catalogues are complete for these magnitude bins. The other side, you can actually approach this more from the source data information, and there are methods around that are based on the probability of detecting earthquakes at given stations, given the magnitude and location of the earthquake and their proximity to the recording stations. And there's a method proposed by Schorlemer and Vosner in 2008 that looks at just at this. It looks at the probability of detecting earthquakes given the noise level at different stations. And this allows us to come up with maps that give us the probability of detection for our stations or in our region for earthquakes of a given magnitude. And in fact, we can turn this around then, and you can end up having, for a given probability of detection, you can end up having maps that show the variation, the time variation in the completeness or the threshold magnitude above which you think your network should be able to detect the earthquake. So this is the completeness problem. And when we're building sort of seismic hazard models that are not necessarily just based on active faults, when building ones that are trying to sort of capture the seismicity in a region, what we're aiming towards here is to try and constrain both the rate of earthquakes, as I said, and the magnitude density function, which we're very, very often using a double truncated Gutenberg-Richter model. So the double truncated Gutenberg-Richter model, we see it in the plot here. It has 4 parameters. It has a minimum and a maximum magnitude. So we're bounding, we're putting limits, magnitude limits on the rate of earthquakes or the probability of earthquakes that we're considering for seismic hazard analysis. We also have then the parameter that describes the rate of earthquakes above a given minimum magnitude, and the ever important B value, the one that describes the relative proportion of smaller to larger magnitudes. But when we estimate the Gutenberg-Richter model, we have to account for the fact that the real earthquake catalogues have a time varying completeness and sometimes also spatially varying completeness. And when we do this, when we try and fit these models using maximum likelihood techniques, we ensure that our techniques are accounting for this this time varying completeness inside of the likelihood function. So this is really the end of the first part of the lecture, or first part of this lecture, looking at how we construct or how we build earthquake catalogues. I want to move on then now to really how we define or how we try and build or construct seismic source models for different PSHA models around the globe. And I'm starting off with one of the very commonly encountered type of model. This is a model based on what we call gridded or smooth seismicity. So the idea here is we're not necessarily just looking at the earthquake catalogue. We're trying to turn this information into estimates of longer term seismic activity rate in a region and account for its sort of spatial variation. So in smooth seismicity models, our main data source is a magnitude homogeneous earthquake catalogue, so the end of what we've just come up with, and that would also include an estimate of the completeness. And we're trying to transform this into a regularly spaced grid of seismic activity rate. And the way this tends to work in practice, this is will be to take our start with our earthquake catalogue. So on the left of these figures here, I have just an idealized example. Here's an earthquake catalogue, various magnitudes, various spatial locations, and we try and translate this into a rate on a regular grid by applying a 2-dimensional smoothing kernel, effectively taking a sort of a kernel, a mathematical function, to take that rate or that earthquake and distribute it relatively uniformly or isotropically uniformly across a grid. And when we sum this up for all of the different earthquakes that are in our catalogue, what we end up with is this smooth seismicity model. So there are different smoothing kernels that are used in the literature. Very often we see isotropic Gaussian kernels or other sorts of Gaussian kernels. And these are parameterized, or these are firstly take as input the distance, the relative distance between your earthquake and your specific grid cell. And they parameterize with a normalization constant, one that sort of ensures that your unit level, your unit rate for an earthquake is preserved when we sum up all the contribution across cells. And particularly important is the bandwidth. The bandwidth is sort of the sigma of this model, which is controlling the amount of smoothing. And it's simply a distance, it controls the distance over which an earthquake is smoothed. How common are these models in PSHA? Well, I'm starting off here just as a sort of a base map showing the 2018 global seismic hazard map from GEM. And if we look at some of the models that contribute or sort of form part of this map or have even been developed since the map, we see smooth seismicity turning up in lots of places. It's common in the US National Seismic Hazard Maps. It's been used in many of the different models in the GEM models for Mexico, Central America, South America. We use them in various different countries in Europe, in Germany, France, Italy, the European ESHM 13 and ESHM 20 models, MA model for Turkey, MCA model for Central Asia, and other GEM models or other models from other authors in Southeast Asia, as well as models in Australia and New Zealand. So you will really encounter smooth seismicity models in most of the sort of large-scale regional models that exist globally. In terms of how we develop the smooth seismicity models, well, the choice of kernel itself can be one issue, but actually the one that has the greatest sort of impact on the hazard itself is how we define this bandwidth. So how we define basically the distance over which each earthquake is smoothed. And you generally see there are two families of models that we see in application. On the right, I'm trying to illustrate here what we have as a fixed width kernel. Basically, the bandwidth of the kernel, of this 2D kernel function, is kept constant regardless of the magnitude of the earthquake, regardless of the location. It's fixed for all earthquakes. This was quite common, including going back to some of the sort of first models that applied this, such as that of Frankel 1996 from the US National Seismic Hazard Model. But more recently, we've seen applications that have used what we call adaptive kernels. So these are kernels where the actual bandwidth itself will change from the earthquake to earthquake. And these might take the form of magnitude-dependent kernels. So based on the size of the earthquake, you might smooth over a different length. But more common or more popular in usage now are nth nearest neighbor kernels, basically ones where the bandwidth is described for each earthquake in terms of the distance to the nth nearest, so the third, fourth, fifth, and so on, nearest neighbor. And the adaptive kernels, particularly the nth nearest neighbor models, are quite effective at making sure that where you have clusters of seismicity or densely clustered seismicity, you aren't necessarily smoothing out over a large distance. So your rate model starts to reflect more the observed seismicity. But when you start to have sort of isolated events or events that are disconnected from the others, then these are sort of smoothed out into sort of a more uniform background. And we can see an example here from the 2018 US National Seismic Hazard Map of these two models in practice. So we have this is a map of activity rates, and we see exactly what I've just described. So on the left, we have the adaptive kernel. So we see clusters or areas of high seismicity, such as the New Madrid seismogenic zone or other areas close to the Canadian border. We have sort of quite high activity rates, relatively well-constrained clusters. And we can contrast this with a fixed width kernel where things are sort of more evenly smoothed out across for each earthquake. How we develop these? Well, the majority of models really require just the earthquake catalog. There are some in the literature that can use faults and moment tensors, and these have been used in existing PSHA models, but the majority are based really just on the earthquake catalog. The choice of kernel function and bandwidth can be optimized through what we call pseudo-perspective forecasting. So one where we split our earthquake catalog into a training period. So we build a sort of a predictive model based on the training period, and then compare that against the sort of the end point of our catalog as a testing period, and try and come up with the best estimate of or the best choice of bandwidth or kernel function. The problem is we have here is that kernel smoothing is actually really only returning the variation in rate. So going back to the first few slides about the two sort of parts of the seismic source model, the estimation of the rate and then the estimation of the density function, which would include the B value, maximum magnitude. Kernel smoothing is only really returning the first of these, just the variation in activity rate, which means to describe the full magnitude frequency distribution, we need other information such as B value, maximum magnitude, or other sorts of focal mechanism parameters. These are usually determined from larger scale zones or regions or super zones and applied to all the cells within each region. One of the big problems we have often in practice is that accounting for the catalog incompleteness is important. So we can't necessarily just take all the earthquakes and just throw them into this kernel smoothing process. And we either need to somehow normalize or weight the earthquakes according to their completeness period, but this can sometimes end up giving you perhaps disproportionately large weights on the smaller magnitudes, which may not be what you want in your model, or limit the catalog only to a complete period and magnitude range, which is perhaps a little bit more sort of fairer, but then you end up sort of really calibrating your model on a relatively short duration of the catalog, maybe only a couple of decades of seismicity. So there are advantages to these types of models. It's a minimal amount of information needed, really at the minimum, just an earthquake catalog, which means that they're possible to apply in most of the world. They are usually reproducible. They have standard algorithms, less expert judgment, and they do account for some uncertainty in the location of future earthquakes. They're also facilitating a move towards sort of time-dependent seismic hazards. So you have seen more models that now start to introduce sort of time-dependent features, sort of ETAS models, also spatial temporal smoothing. So this does begin to move in that direction. But in the meantime, they're useful for background seismicity, and the biggest advantage is that they are, they're considered as data-driven. However, they're also considered as data-driven, and this is not always an advantage. So limitations in your data, whether it's poor estimates of magnitude, location uncertainty, miscalibrations or bad estimates of completeness, this will have a large influence on the resulting seismicity patterns, and something one has to be really quite aware of when one applies these. There are a limited number of configurable parameters, so you might find that the pattern of seismicity or the forecast is doing very well in one region, but not another, but you don't easily have dials that you can adjust, so you end up having to sort of really try and tune or calibrate just the few parameters that you can control. And it's highly sensitive to completeness, especially for when we start to use sort of nth nearest neighbor adaptive kernels. Arguably, the biggest criticism behind this, though, these models are, though, that they are a form of historical probabilism, that they are making sort of predictions of long-term earthquake rate that start to become really heavily dependent on the observed distribution of earthquakes, mostly within the last sort of few decades, and not necessarily of the longer-term process. So there's plenty of room for surprises and to be caught out. And the other problem we have is that it only yields activity rates. We need other information to constrain the full distribution. So this then covers sort of one of the most common types of source models we see in practice. I'm focused then on another type of source model that we see in practice a lot, which are these area source models. Well, why do we use these, or why would we try and define these? Well, I'll start by considering the case of Germany. So Germany is an area of, say, low to moderate seismicity, at least in a global sense, and it's an area of low tectonic deformation. But there are notable active tectonic structures that have produced seismicity, including damaging seismicity, even in the last 100 years or so. So these include the Rhine-Graben, Alps, the Vogtland on the sort of Czech East German border. And if we try and compare the seismicity with maps of geology, so structural geology, it's quite hard to reconcile the two. It's hard to easily sort of pin or attribute the faults, the seismicity to particular structures, except maybe in those most active areas in the Rhine-Graben or southern Germany. And in terms of being guided just by the seismicity, well, we have really about a 1,000-year historical catalogue, and with really very little information prior to, say, 1500 or 1600. So this is really too short to capture the very long-term seismic cycle that's clearly taking place in Germany. So in terms of trying to characterize the seismic sources for seismic hazard analysis, we then try and rely on analysts or experts to sort of interpret not just the seismicity, but all of the available data. This includes all those other data sets that I was mentioning in the first few slides, including geology, other sorts of geophysical data sets, stress, strain, etc., to define a set of zones that represent what we consider to be the likely sources of future seismicity. And this includes defining their scale, so basically large scale or small scale, their actual boundaries where the edges of the zones are, and with that, the distribution of the parameters that are relevant for characterizing seismicity in the zone. So recurrence parameters, parameters on sort of likely orientations of the ruptures, and so on. And seismicity within each zone is usually assumed to be uniform. This would be quite a challenging thing to do in practice, and it's quite a subjective process, and one in which we tend to try and engage not just sort of one person, but we try to engage a variety of different perspectives to construct these models. So, for example, here, there's a very good example here from a paper by Villanova et al. 2014, where we have, for example, an idealized situation. We have sort of two different geological environments, a quaternary basement and crystalline basement, and you have some seismicity. And we're asked then you'd ask perhaps different experts to define or delineate zones for this region. And you consult 3 different analysts, and the analysts might come up with different perspectives. So analyst A says they prefer to delineate their zones based more on the observed spatial patterns of seismicity. So their zones start to reflect different sort of clusters or different sort of spatial trends that they might see in the data. Analyst B believes the geological domain is more important, so their zonation starts to reflect more the underlying geology and less of the observed seismicity. And analyst C may want to aim for a balance of the two, so recognizing the geological domains are primary, but also seeing or dividing the zones according to seismicity as well. And different perspectives emerge, and you can have perspective where some analysts would prefer to go for larger scale zones, so they're not trying to model necessarily every single feature, or they may assume that seismicity is more uniform within a tectonic unit, or you might find experts referring to smaller scale zones, so ones where we really try and capture a small scale variation in seismicity. What's important about this is, so we see, for example, on the slides on the left, these are 4 models that have been used in the recent 2018 German seismic hazard model from Grunthal et al. And although there are different perspectives that go into each one of these zonations, what we do see is that where data sets converge towards similar interpretations, the actual area sources begin to look quite similar. This is for example, all of the models cover or have very similar sort of sources that cover the Rhine-Graben, cover the Alpine Faultland, the Alpine Foreland, sorry. And where we have quite different interpretations, we clearly end up with very different or different sort of zonations. But that's really reflecting how certain or how uncertain we are, or the community is about where the actual seismic sources are, which is kind of a desirable feature of how the models should work. Our model-to-model uncertainty should be greater where we have less information or less data to constrain them. So where are PSHA models? Where are area sources used in PSHA? Well, again, starting with our base map, we see them used in Canada. This is quite common in the last few generations of model. Notably, they're not used in the United States, at least not for the last couple of generations of models, but you do find them in hazard models in GEMS database for Central America and the Caribbean. And when we go to Europe, you see them really in all the national models, and the European models will have some source models that are area source model based in the UK, Germany, France, Italy, at the European scale. They've been used in sub-Saharan Africa by PSHA et al., been used in Central Asia, but in the EMCA model, in India, and also in Australia as well. So again, much like smooth seismicity, these area source models are used really across the world. They have advantages, so they allow us to sort of delineate sources incorporating a wider variety of data, so seismicity, geology, tectonics, geodesy, more than just the one data set from seismicity. And they sort of reduce the degree of historical probabilism. So you can make interpretations based on longer scale geology and tectonics rather than just the observed seismicity. They can even be used to represent or characterize active faults or fault systems if the faults themselves can't be fully parameterized for what we need in PSHA. Larger scale zones may provide enough seismicity to provide sort of zone-specific recurrence models. Otherwise, we may sort of start to group models together into sort of larger super zones. And as we've seen, alternative interpretations can be accommodated in our epistemic uncertainty analysis. So we should have more uncertainty where we have really less agreement in the community. The biggest limitation or the biggest sort of objection to these tend to relate more to this issue of subjectivity and lack of producibility. So it becomes very harder to necessarily sort of reproduce a particular expert's interpretation or workflow. And we may need many models to cover a range of interpretations. And sometimes we may end up having sort of over-interpretation, too many zones, each with too few data, or under-interpretation, sort of large areas of uniform seismicity. Can we actually try and address this in a certain way? So there have been sort of examples where automatic procedures have been created for delineating seismic zones. And these have been done using sort of cluster analysis or unsupervised learning methods. These could be more sort of theoretically objective and reproducible. So given the same data and the same settings, another analyst could build the same model. But the problem here is that they tend to require the definition of an objective function, basically a function that tells us this is a good or a better fitting model or a poorer fitting model for our purpose. And how you define these is firstly not easy, and secondly actually quite subjective. It depends on your own sort of perspectives. So, and it's also very difficult to optimize the number of zones and their geographical extent. It's quite a difficult or a sensitive problem. So if we can't like automate this process or make this reproducible, can we at least use forecast testing to see which zonations fit better to data? And the answer to that is yes, this is being done more in practice using methods from the Collaboratory for the Study of Earthquake Predictability, or CSEP. And this has been used in recent models in Italy and in Europe. But there is a caveat to that, which is that testing periods are usually quite short. So usually only a matter of a few years. And even in active regions, these sort of CSEP style tests, so often sort of likelihood-based tests, tend to favor more models that are based or capture more close to the last couple of decades of seismicity rather than those that are based on long-term geological processes. There are obviously many different cases, but I would say they would tend to lean more towards capturing the last or the most recent seismicity. One last issue we deal with when we're dealing with these gridded seismicity sources and area sources is that we actually, even though we don't necessarily have actual finite fault surfaces, our ground motion models require that the rupture itself or the fault itself is characterized not as a point, but as an actual finite fault. And what we do in practice is to actually then, we try and use information to create what we call virtual faults. So these are sort of virtual or synthetic planes that try and capture where we think what the future faults might look like. And we can account, for example, for different, many hypercentral depths within a zone or within a grid source, and many different orientations of the fault, where we really have very little constraint on what sort of strike or dip the fault should take. So grid sources and area sources require this information to control how these virtual faults should behave. And exactly how this works is something that differs from one PSHA software to another, and could be a different way. You might have differences in seismic hazard results, even from the same source model. But they also require that when we're building our source models, we need to have more information, or start to provide more information about how the rupture size scales with magnitude, about the sort of likely orientations of faults within the area or grid seismicity zones. And then this brings us on then to our last sort of main type of active fault source that we use in PSHA, which are the actual active faults themselves. So these are the three-dimensional fault surfaces that become then the locations of future ruptures. And again, we're starting off with fault geometries. So we actually have, for example, these are many different examples of fault geometries supported by currently the OpenQuake PSHA software. And most modern PSHA software can accommodate representations of faults with a relatively high degree of flexibility and sophistication. So anything from simple planar surfaces to sort of multiplanar surfaces to sort of complex discontinuous surfaces or district faults and so on. In terms of how we characterize recurrence, so fault recurrence models are usually moment balanced, which means that they're constrained by not by seismicity necessarily, but actually by the geological slip and the size of the fault surface. And from this, you might consider several different types of recurrence models. So you may encounter sort of characteristic models. One's usually associated with a full rupture of the full fault surface. And these may be sort of single magnitudes, a single characteristic magnitude, or they may account for some uncertainty in the magnitude for the size of the rupture by sort of in the form of a normal distribution. You might also encounter the case where we actually expect that the fault rupture may be smaller than the fault surface itself, in which case we may have to allow for different locations of the rupture and many smaller magnitudes on our fault. And this is the case when we tend to turn towards exponential or hybrid characteristic models. So models that do allow for smaller magnitudes than the total rupture of the fault surface, but they may or may not have an increased probability or increased likelihood of a characteristic earthquake rupture. Generally, the seismic hazard models are quite agnostic on the debate of sort of characteristic versus non-characteristic, but we do rely on the geologists to try and provide the best information they can. How do we parameterize these models? How do we build active fault models in PSHA? Well, one of the approaches that you might encounter in practice are based on what we call composite source approaches. I won't go into too much detail, but largely they begin with an interpretation of the fault geometry or the observations of displacement and slip, and to try and from this geometry create a sort of an idealized surface, an idealized single trace, and then an idealized three-dimensional surface. And for that surface, we're to assign an average or preferred geometry or average properties or distributions of properties such as slip rate, maximum magnitude, coupling, etc. And within these sources, they tend to allow the possibility that ruptures can be less than or equal to the composite source length. So they're a little bit better suited to, say, exponential models or hybrid recurrence models than they are to purely characteristic models. And you'll see these sorts of models applied in Europe quite often, in the European hazard models, in Italy, in Turkey, and other national PSHA models. At the other end of the spectrum, we have active faults, or you could actually try and model faults more from a fault system perspective. And this is where we really see the state of the art that's been emerged from recent years in California coming into place, of one where we sort of start to begin to discard or reduce these previous assumptions about segmentation, and you start to break the fault system down into sort of large numbers of small sections, and you try and constrain the slip rate and the geology more sort of a more nuanced basis. You can constrain it for each section from geology or geodesy, and you begin to build rupture sets by looking or applying criteria that might allow ruptures to form, and try and solve via what we call a grand inversion. So constrained by sort of slip rate, paleoseismic event rate, and regional seismicity, try and constrain then the rates of the ruptures and the resulting probabilities of the different ruptures. And what you end up with here is are outputs that take the form not of a fault source model per se, but of an earthquake rupture forecast. So a set of ruptures and their associated probabilities of occurrence. I'll skip a couple of slides here on how we try and balance faults and regional seismicity, because time is moving ahead, to focus a little bit on modeling uncertainties. This is the last topic before I begin to wrap up. So we can talk about modeling uncertainties. In seismic hazard analysis, we've often always try and split our uncertainties into sort of two forms of uncertainty. One is aleatory variability. And this describes sort of random outcomes from natural variability in a process for a given model formulation of the process. So this is something we consider to be an irreducible uncertainty. So in terms of source modeling, this would consider an aleatory variability would be the magnitude of the next earthquake, or the location of the earthquake, or the size of the rupture, or in ground motion modeling, the amplitude of the ground motion at the site given the rupture. And each complete seismogenic source model we build is actually a model that's describing in these probability distributions the set of aleatory uncertainties relating to the earthquake rupture. But this contrasts with the other definition, or the other uncertainty we encounter a lot, which is epistemic uncertainty. So this is the lack of knowledge about the models for the state of nature. And these should be more reducible with data, so we might choose which models are better for our region once we have more data or better understanding of physics. And in practice, we capture these alternatives using a logic tree approach. We might consider multiple models or even parameter uncertainties and assign different weights to these. So different models you may encounter in practice by epistemic uncertainties by source. So for example, for smooth seismicity, you may encounter epistemic uncertainty in your base data. For example, you may have different catalogs for a region, and you may want to consider both of them, or you may have different catalog processing procedures for completeness or declustering. Quite often, in most cases, you would see epistemic uncertainty to account for different smoothing kernels, or so either whether it's fixed or adaptive, or different bandwidths or different ways of constraining the bandwidths, and different models for recurrence properties. So you may have different models of rate, b-value, Mmax, and so on. For uniform area sources, actually many of the same epistemic uncertainties apply. So uncertainties in your catalog processing, your recurrence. The only sort of major difference here is that we would account for epistemic uncertainty in our area source zonation. So we may choose different interpretations of the geology, seismicity, and tectonics to try and account for our model-to-model uncertainty. For fault sources, we start to get a little bit more complex area. So we might, starting with the geometry of our source, we may account for epistemic uncertainty in terms of the actual source geometry itself. So different values of dip, values of seismogenic thickness, or in the more complex models, we may have to account for epistemic uncertainty in the sorts of connections or the connectivity of the fault. So which sections may rupture together, and what's the likelihood of these. Very often you have epistemic uncertainty on your slip rate and coupling. So you may have different constraints on your slip rate, or even the distribution of slip rate. And from this, you may end up having epistemic uncertainty in the distribution used to characterize your long-term rate. So whether you choose to have just a sort of characteristic distribution or an exponential or some mix of the two. And at the end of all of this, if you actually have relatively well constrained or parameterized faults, we have this issue of calculating or constraining long-term probabilities. So these are our probabilities in the next sort of 30 or 50 years based on time-dependent models, where you may have epistemic uncertainty on the aperiodicity of the model, the choice of model, maybe even the date since the last event. And I haven't really mentioned this here. This could be a whole other topic in itself. In fact, I think there's been lectures on this already. The role that geodesy has to play in here, and it can actually play several different roles and that are varied from model to model. But I'd say it's becoming most commonly used as a way of sort of direct inversion of, or by directly inverting on GPS velocities to yield estimates of slip rate and in terms of sort of strike normal or strike slip rate on our faults. And this can also be used to constrain slip rate and moment rates, which also allows to then be able to sort of separate out on-fault strain or input from off-fault strain. And the off-fault strain can help us sort of capture some of the off-fault deformation and the background seismicity. So this has really been a sort of 45-minute or so sort of general overview of really how we approach sort of PSHA, seismic source modeling in PSHA. So I'll just end on a few sort of thoughts about where we are right now and what's the sort of future of the field. So it's the end of 2021 is actually quite an interesting sort of point to sort of stop and take perspective of what we actually have in terms of global sort of hazard models around the globe. So for example, we have in 2018 the GEM global hazard model and database of PSHA models. And this covers the entirety of the globe. And most of the models here are sort of represent a sort of broad application of relatively well-established methods and processes for PSHA source modeling. So this is really sort of trying to bring a lot of the world up to a good or a solid state of practice. And I think it's done that it's been incredibly hard work, and they achieved that brilliantly. More recently, for example, in the Section 20 European model, but also in national models in Australia, Canada, Italy, France, and so on, you start to see new methods kind of coming into play for making advances and improvements on established methods, so particularly for characterizing uncertainties. In those regions of more active seismicity, where we actually have fault sources, these are now becoming more routinely represented in the national regional models. So we see this in Japan, Taiwan, China, Indonesia, Southeast Asia, and the USA, excluding California. And I say excluding California because this grand inversion process that I've gone through in a relatively short period of time, this user-free approach, is really a sort of a step forward. It's a sort of state of the art. It's being used already in California, and it's currently being in use for the next generation New Zealand seismic hazard model. And we're also starting to see some models begin to explore or have more routine estimations of time-dependent PSHA, both in terms of long-term and short-term time dependence. For low to moderate seismicity regions, a lot of the effort or the focus here has been on characterizing uncertainties in the estimation of earthquake recurrence and really making sure we're effectively propagating all the uncertainties that we have from instrumental and macroseismically inferred locations of magnitudes into the recurrence model. So we're starting to see a bit more use of Bayesian methods that account for some of these uncertainties. Some models have started to include active faults. We've seen this in the Rheingraben in Germany, you've seen it in Australia. But in regions of low seismicity or low deformation, there become a lot of open questions. So how to manage the large uncertainties on the fault slip or recurrence? What do we do with the evidence of, say, quasi-periodic behavior, so cycles of higher or lower activity, and how do we bring these into PSHA? These are sort of ongoing questions that have begun to be addressed in some models. For more active regions or regions where we do have good constraints on fault models, well, really, as I said, this user-free, this grand inversion is a paradigm shift for seismic source modeling in PSHA, and we're likely to see this expand to other regions in the next 10 years or so, where the data allows. It's currently ongoing in New Zealand. It may begin to emerge elsewhere. And with this, we have a bit more exploration of the epistemic uncertainties in the fault behavior. Particularly interesting or relevant are fault interactions, sort of clustering, time dependence. PSHA software can cope with this now, and several different PSHA software can accommodate these sort of rupture forecast models. So they have sort of large rupture sets and mutual exclusivity. But how we constrain these probabilities of interactions and these clusters and so on is an area of active research. And the next generation California model, USER4, is placing the emphasis on the use of physics-based simulators for this purpose. And another way in which we can sort of look about how seismic source modeling may go in the future is to look at the role that Fault2SHA can play in this. And I'd say this is something not to be underestimated. It's a large organization now. It has a joint organization of geologists, geodesists, seismologists, hazard modelers. It's doing state-of-the-art, it's producing state-of-the-art data and research around the natural laboratories, so Apennines, Betics, and maybe some others to follow. It's producing tools that are there to put these ideas into practice, so sort of fish, sheriffs, and sunfish and other. And it's working independently of specific PSHA projects. And I think this is a really strong advantage because with PSHA projects, we're often sort of limited by deadlines, by resources, by sort of trying to understand the implications in terms of the outputs, which doesn't always allow us so much freedom to explore new ideas and new science. So I think in terms of where the future of PSHA modeling can go is to look at engaging with Fault2SHA is a good way to sort of guide or steer that. So I'll stop here and thank you all for your time. I'll give you one last recommendation, a little bit of recommended reading for those of you who are sort of interested to go more into seismic hazard analysis. At the end of last year, a new textbook on seismic hazard analysis was published by Jack Baker, Brendan Bradley, and Peter Stafford. And I really can't recommend this highly enough. It covers an extensive range of topics of many aspects of seismic hazard, state of the art, both in theory and practice. And it's freely available. It's available from your distributors, Cambridge University Press, Amazon, and so on. And a couple of other recommendations for recommended literature. There have been in the last year or two some good review papers on sort of current state of PSHA at regional and national scales, one focusing on PSHA in general, another focusing on active faults in particular. So the PSHA one by Gerstenberger et al. In reviews of geophysics, and the fault and tectonics ones more from Morel et al. In tectonics. And these are both give really good overviews on sort of where we are right now and where we could be going in the future. And with that, I will say thank you very much. And I hope I might be enough for a couple of minutes for a couple of questions if there are any. So thank you very much.
Thank you so much, Graeme. That's been a really useful sort of summary and hopefully has helped a lot of people understand the connection of the work they're doing to how it all comes together for the hazard modelling. Does anyone have any questions that they would like to ask Graeme? Either raise your hand, speak out, or if you want to put in the chat, we can read that as well. I have one question, which I think I'm not going to expect you to ask fully today, answer fully today, Graeme, but to me, a crucial problem does seem to be, and an exciting opportunity as well, is how we go from the models and testing them. And you alluded to this a lot throughout your presentation, that we base it on past data. So then we can only test it, I guess, with future events. And, then we learn more as each event happens. But where do you think we're going in terms of producing our models and then actually being able to test and compare, which models might be more suitable, which are good models, which are less good? Do we just combine all of them? Where are we, do you think, in that?
It's a really important question and a really sort of relevant topic. And this is that we're looking at this from various different aspects in the sort of seismic hazard model community. So, for example, a lot of emphasis has been placed on sort of testing earthquakes as sort of forecasts, effectively, and as sort of forecasts of the rates of occurrence of ground motions, and from that to try and make estimates or try and sort of test these or subject these to sort of classic sort of forecast testing processes based on your observed, so let's say the last sort of 5 years or maybe 10 years or so of observed ground motions, or perhaps over a longer period of time if you try and sort of bring in macroseismic intensity back into this process as a constraint over longer periods. So there's a perspective that says, okay, you're trying to sort of fit the PSHA into a forecasting framework. PSHA is predicting the probability of or the likelihood of exceeding level of ground motion, so we can try and test them in that way. It's a really very challenging and very often a controversial sort of approach to do that, because you're really limiting, or you may end up sort of, firstly, we don't always have great data in a lot of regions to do this. Our data, even our observations, are not perfect representations of everything that's happened. And very often I could think of my head right now of several papers where I've really sort of felt they haven't always tested like with like, that they may be neglecting or overlooking sort of issues or limitations of their data set and treating as an objective truth something that has already got some problems and interpretations in it. And even then, as I said, one of the challenges you have is that the sort of the reference point or which you should be sort of comparing forecast skill should be against persistence. And what that really means is that very often these sort of forecast testing procedures end up giving a lot of favor, a lot of weight to those models that are capturing the last 10, 5, or 20 years of seismicity, and in doing so end up sort of down weighting a little bit those models that are based on the geology and tectonics, when that isn't necessarily serving the purpose of what the engineering community needs. I mean, what we need for engineering is not necessarily always the best estimation in the next 5 years. We need to sort of estimate, okay, what's the likelihood of exceeding ground motion in a 100-year period or 200-year period, or so on and so on. So so those sort of forecast testing processes don't always provide that answer, or they can do it with several different biases, which is not to say they don't have use, that they really do, but they have to be treated a little bit carefully. Where you are seeing sort of, and you have seen in the last 20 years or so, this question of testing coming in has been on the use of precariously balanced rocks or precariously balanced features. So these are sort of geological features in an environment where they could be sensitive to shaking, or at least because you can sort of more or less calibrate the sorts of ground motion levels that would expect this geologically balanced feature to topple. You can then provide a ceiling on terms of, okay, if this hasn't toppled within the last sort of 20,000 years or 50,000 years, this would perhaps indicate that this level of ground motion, the level of ground motion that would be required to overturn this geological feature, has not been exceeded. And this has been a really important development in the field. This has really sort of led there's a classic paper by Anderson and Brune, I think in 1998, that's really sort of led to the changes in how we characterize PSHA in terms of going towards what we call non-ergodic approaches, where we start to begin to try and remove those pieces of uncertainty that we've kind of introduced over the years from having to aggregate data on large spatial scales, and start to begin to say, okay, how can we calibrate specifically the uncertainties for this region or this site? And this is something that's come from really seeing that we have perhaps in the past, by having these large uncertainties, ended up with overestimations of activity rates, or overestimations of rates of exceedance of ground motion, compared to what we've seen from these precariously balanced sort of rocks and geology. So this has become a really important area of research and application. There are some fantastic papers on using how to use precariously balanced rocks for for testing PSHA, and they give us a window into longer time scales. They give us a picture of sort of thousands of year time scales, not necessarily sort of a few hundred years. But there are also caveats and limitations there. Most importantly, you don't always find these features in every geological environment that you need. They've been definitely well applied in California, I think in New Zealand and in parts of Europe, but they wouldn't necessarily always work, or you don't necessarily have the right sort of geological environment to really find these features. If I was to look at, for example, parts of Germany or parts of the UK, we wouldn't necessarily see these features there that we can always identify. So there are still many challenges behind that, but that's been an influential area of testing as well. So there's different perspectives. There's probably a lecture that someone could give in the future on to give you a much more detailed answer on that one, because it is an interesting and active area of research.
Great. Well, thank you so much, Graeme. I think we're going to have to leave it there. Thank you, everyone, for joining. And we look forward to joining you next time. But for now, Graeme, thank you again so much for your lecture. Really appreciate it. Lots of insights, and see you